Our next speaker will be Sabine Wollmann from the University of Bristol, and she will be talking about experimental demonstration of robust quantum steering. Go ahead. Let's teach us about quantum steering. Thanks.
Thank you for the introduction. Let me go into presentation mode. Yeah, thank you for the introduction. I'm going to talk about experimental demonstration of robust quantum steering today. And this is a project I worked on together with Rupola from the University of Geneva in Switzerland and Ana Costa from the University of Paraná in Brazil. I would like to acknowledge the financial support which we received from the Center for Quantum Computation Communication Technology and the Griffith University, both in Australia, and EPR-steering in the UK. And I also would like to say thank you to the organizers of the Q-Turn 2018 workshop that supported this project with a travel grant. So I think we're quite united on the fact that entanglement is the workhorse for many experiments in quantum information science. And the kind of experiments I'm talking about usually consist of the joint preparation of a bipartite state, which we share between observers Alice and Bob. And they can then perform a set of measurements on their part of the state. And then after they've done this, they can report the classical measurement outcomes, and they can compare these and try to see if they were able to observe some correlations. And that fourth experiment was described by Einstein, Podolsky, and Rose in 1935. And they struggled a bit explaining these kind of observations they made, and because they were not able to explain it within a local realistic framework. And that's why they said Alice must cause some spooky actions at a distance on Bob's quantum state. So many years later, John Bell gave us a mathematical tool, which is known today as the Bell test, that allows us to test for these correlations.
Sabine, I'm afraid you're not sharing your screen yet. Can you try?
Oh.
Thank you.
Let me do this. Can you see it?
Yes, now we can see it.
Perfect.
Great, thank you.
Okay. I don't want to hold away the workhorse I mentioned. And so here we see the joint preparation of the state, which we share between Alice and Bob. And here are also some lovely pictures of Einstein, Podolsky, Rosen, and John Bell. Okay, so this all led to the definition of non-locality classes. And so in a Bell test, we make no assumptions. So assumptions is always the equivalent of trusting our observers. So and that means in a Bell test, both observers, Alice and Bob, are sitting in black boxes. So we don't know what kind of measurements they're performing and what their measurement devices are doing. So on the other side of the spectrum, if you would fully trust both observers, then you know exactly what they're doing. And this is what's happening when you measure an unentanglement witness. And intermediate to these two classes is EPR-steering. And EPR-steering is an asymmetric protocol. So you make assumptions about Bob, so you know exactly what he's doing, the measurement settings he's using, what his device is doing. But you don't know anything about Alice, so she's still a black box to you. And so Bell tests are really cool protocols, and they're actually the most rigorous test for us to test non-locality or entanglement in any protocol. However, performing it is experimentally quite challenging, and you can see that simply by the fact that a loophole-free detection of Bell non-locality was done in 2015. And if you compare it to the EPR-steering protocols, they were experimentally demonstrated the first time in 2010, so quite a while earlier. And the reason for that is because EPR steering protocols are much more robust and noise-friendly when you perform them in experiments. So it's quite clear to us that bell tests are what we desire to do in experiments, but actually EPR steering protocols are what we are capable of doing at this point. So what we wanted to do in our experiment, we wanted to bridge this gap. So we want to bring steering protocols a bit closer to bell tests. And we wanted to do this by lifting remaining assumptions which we make in our steering protocols. And for this, we tested experimentally tested two promising classes of steering criteria. So the first class was based on entropic uncertainty relations based on the Shannon, Sellis, and Renyi entropy. So this might look quite familiar. So if Q converges to 1, then you have the very familiar Shannon entropy. If Q is 2, then you have the Sellis entropy. So this is an easy way for you, just by changing the parameter, how you can go between the different entropies. And so this kind of class of steering criteria is really cool because it allows for detection of steering over a really large class of the 2-qubit states. It can be easily extended to higher dimensional states, and it provides some advantages in terms of detection of over linear steering inequalities. So the second class which we investigated is dimension bounded steering inequalities. And they're really cool because what they're actually doing is they remain assumptions on Bob's side. So they make Bob's measurement devices, they turn them a little bit more into a black box by removing assumptions on what kind of measurements they're performing. So they're simply taking Bob and turning his measurement device into a simple click or no click qubit measurement. So these are the two classes which we investigated. And further, we wanted to consider some noise in our experiment. And we did this by investigating misalignment in a reference frame. And what we mean by that is, so in the first example here on the left side, so you see a perfectly aligned reference frame between Alice and Bob's measurement settings. So they're perfectly aligned, and we know in such a scenario we can easily demonstrate steering. But quite often you're especially when you're in an experimental situation, achieving this perfect alignment is not that easy. So it's usually easy, for example, to maintain your orthogonal polarization, but when you guide light through a fiber, it might start rotating a bit. So it's not that trivial to establish this. And then the question is, can you then still demonstrate steering? And the answer is yes, for certain steering inequalities, the answer is clearly yes. And because this is a very promising aspect, we wanted to investigate that, as establishing this, as I said, is really either resource intensive or experimentally challenging, and still quite a challenge in quantum communication experiments. So to test a EPR steering protocol, you perform a steering task. And this here is how our steering task looks in more detail. So it's a multi-step process. In the first step, you share a state between your observers, Alice and Bob. And at this part, they are not able to distinguish if they have received part of her entangled state psi AB, or if Alice has simply shared a single qubit to Bob. Next, Bob chooses a measurement setting, and he publicly announces the measurement setting. Then he performs the measurement, and he secretly records its outcome. And then the next step, Alice publicly announces her measurement outcome. However, we don't know what she did. So she's a black box to us, and because of that, we don't know if the measurement outcome is the result of a genuine measurement, if she might have tried to cheat on us, or if she might have even lost her photon and was not actually able to perform a measurement. And then in the end, Bob takes all this information together, and he's calculating this correlation function here, which we call the steering parameter S. And we compare this steering parameter against the classical bound. And if the steering parameter is above the classical bound, then we know the shared state was entangled. If it's below a classical bound, then we can't say so. So to perform that experimentally, we have built a CW pumped Sagnac ring interferometer. So here on the top, you see the 410 nanometer laser entering into the experiment. The light is then split between the two paths of the interferometer, pumping a PPKTP crystal and generating down-converted photons at 820 nanometers. And then, then they're interfering at this PBS again, so you erase the path information, and then you're sending the photons to Alice, which is here, and Bob, which is over here, and both parties have the appropriate polarization analysis tools in form of wave plates and their polarizing beam splitters, and then in the end, you're sending your photons to detectors, and in this experiment, we used APDs. So the first measurement setting which we investigated in this experiment is 2 measurement settings per size. So this is the minimal set size for steering protocols, and you can see the measurement settings here and pointed out in these block spheres. I would like to say throughout this experiment, Bob's measurement settings remained constant. So he always kept on measuring along sigma Z and sigma X. And for Alice measurement settings were orthogonal to each other. However, they were not necessarily aligned with Bob, so we were able to rotate them either within the same plane or even by tilting out of the plane. And for this experiment, we considered that we shared a Werner state between Alice and Bob. And the Werner state is parameterized by the Werner parameter mu, which ranges between 0 and 1. So if the Werner parameter is 1, then you have a maximally entangled singlet state. And if mu is 0, then you have a maximally mixed state. And for 2 measurement settings per site, and for such a shared quantum state, our inequalities take on this form. So as I said earlier, so they have this form here. And if Q is 1, then this is the inequality based on Shannon entropy. And if Q is 2, then you have the inequality based on the Zellis entropy. Here we see the Renyi inequality based on Renyi entropy. And here on the bottom is the dimension bounded steering inequality. So these are the inequalities which we tested in our experiment and compared to each other. So first, we assumed we had one shared direction. So this means Alice and Bob's measurement settings lie within the same plane. However, it might not be the case that that their orientation within this plane is the same, which is denoted here by seeing these dots. So Alice measurement settings can take on any of these dots, but they have to remain orthogonal. Ooh. So that are the results for this experiment. So we can see that all our inequalities allow us to demonstrate steering. The dimension-bounded steering inequality is rotation invariant, so it's completely independent on this angle alpha by how much you rotate your settings within the plane. And your entropy-based inequalities are dependent on alpha. So there are certain values for alpha. If you overcome them, you can't demonstrate steering anymore. So next, we started tilting our measurement settings out of this plane. So we increased this angle phi from 0 to 30 degrees. And we can see this is exactly the same case. So we're still able to demonstrate steering. However, our robustness in violating this inequality, or the bound of 0 is starting to shrink. And then finally, we tilted completely out of this plane. So we had 90 degrees, which means we have no shared direction anymore. And for this case, none of these inequalities will allow you to demonstrate steering. So you lost this. For completeness reasons, we extended this experiment from 2 to 3 measurement settings. And this means we used an additional third measurement direction, and this is the green one here. So it's a measurement along sigma y. And again, we went through all the different angles. And so what you see a very similar behavior. And if you've gotten a bit lost, then I think this is now the moment to wake up again. So this is, I think, the plot C here on the bottom. This is the take-home message. So just by extending the number of measurement settings from 2 to 3, still allows you to demonstrate steering when you were not able to do this before. So we clearly see here on the bottom, by using the dimension-bounded steering inequality, and despite having no shared direction between our observers anymore, we can still demonstrate steering. So I think this is really cool, and I think this clearly shows that dimension-bounded steering inequalities could be a really interesting case to be used in quantum fiber networks. And because of that, we went a step further. So we felt like we also would like to know now what's the probability of success when you use this steering inequality. So we calculated that. And here we see the plot that shows us the probability of violation against the Werner parameter mu. And so what we see here, if you use two orthogonal measurement settings, which you're now allowed to randomly choose across your block sphere, then you can see you have a 66.7% success rate of violating this inequality if you have a perfect singlet state. And if you use 3 random orthogonal measurement settings, then you can even achieve 100% success rate. So as long as your shared state between Alice and Bob fulfills this condition here for mu being equal or bigger than 1/√3. So I want to come to the end and wrap up. So what I showed you in this talk here is the first experimental demonstration of quantum steering based on these generalized entropic steering inequalities and dimension-bounded steering criteria. We also considered misalignment to a shared measurement reference frame, so a very natural problem in experiments. And we identified a really cool suitable candidate for near-term quantum applications. So I want to say thank you, and if you want to have any more details or information, and I would recommend you to check out this paper here on the archive. Thank you.
Great talk, Sabine. Thank you very much. we have a first question from Mehul Manik. Great talk. Can you explain the dimension boundedness a bit more? Does it bound the dimensionality of entanglement as well?
Yeah, so it's actually, so the steering inequality is really cool. So it's actually exactly exploiting this. So it's a three-step process where you actually use dimension-bounded entanglement criteria and you apply them onto these quantum states to achieve a dimension-bounded steering inequality.
Okay, great. I actually have a question of my own. Do you know if there are any protocols already which use these type of steering elements in it, which are actually being tested as a QKD protocol?
You mean applications? Like?
Yes, if there are actually people doing experiments trying to build actual QKD or quantum communication systems based on these types of inequalities.
I know of some ongoing experiments, but they are not published.
Okay. So it's definitely becoming closer to being applied there. And also, are there any other applications for this next to quantum communication?
I think quantum communication is the most obvious and strongest candidate. You can think about potential applications in quantum metrology, where you want to measure or sense something which is out of your reach and you have no control over. So that could be interesting as well. I know there are some theorists working on this.
Okay, great. We have another question, which is from Vatsal Srivastava. In this reference you mentioned, you also deal with the loss in MUBs. How does it affect the dimension bound? Could you elaborate a bit?
I'm not quite sure if I understand the question.
So it asks about a loss in MUBs. I'm not quite sure what MUBs refer to. Do you?
Yeah, so he wants to, okay, so I think he wants to know what's happening when you stop only considering orthogonal measurement settings, so mutually unbiased bases, and when you start to consider non-orthogonal measurement settings. So we actually analyzed or measured this as well, and it's in the supplemental material of the paper I pointed out, and you can see even then you can still violate the steering inequality, and even if you have three non-orthogonal measurement settings which are completely misaligned between Alice and Bob, even then using the dimension-bounded steering inequality still allows you to demonstrate steering.
Okay, interesting. Yeah, I think we still have time for another question. How have you tried this this type of steering with different types of encoding?
So you mean like going from polarization and, for example, time or path?
Yes.
Yes. So actually, I'm working on another steering experiment at the moment in collaboration with Paul Skripczyk and Andres Tucaro. They're both from the University of Bristol, and we use a different kind of encoding. In that case, we use path encoding because we use a 2-qubit silicon chip, and the way of encoding information there is done in path.
Right, interesting. Good. I think let's continue discussion about this talk on Slack. I think we're currently watching with about 134 people, so we're quite a crowd looking at this. Great talk so far. Thank you.